Welcome to MECH 2311 Thermodynamics 1. This is a video lecture covering Module 6, the second law of thermodynamics and entropy. This is a very wide topic within thermodynamics, and there are two chapters in the textbook that we will discuss. The topics in two chapters will be discussed. I have listed the section numbers here for your easy reference, and we will stick to the topics only in these sections and try to keep it as simple and uncluttered as possible. Now, let's begin our discussion by asking a simple question. What is the first law of thermodynamics? Like, what did we learn as the first law of thermodynamics? If you state it in words, that would be energy can neither be created nor be destroyed. It may be transformed from one form to another. If you write it in terms of symbols, we wrote it as Q minus W equals delta U plus delta KE plus delta PE. Or if you write it in the intensive form, this is Q minus W equals change in internal energy per unit mass plus change in kinetic energy plus change in potential energy. This statement, the first law of thermodynamics, tells us an account or balance of the energies. It merely implies that if you apply heat or do work, you can cause a change in the energy of the system. I'll just write internal energy and leave the other two for simplicity. And you can do work, change the internal energy. You can transfer heat, change the internal energy, and so on. Now suppose, let's say you have a hot cup of coffee that is at, let's say, 120 degrees Fahrenheit, and the room is at something like 70 degrees Fahrenheit. You do know that what will happen. The coffee will lose its heat if you leave it and come back after some time. Eventually it will reach the same temperature as the room. All the heat energy that the coffee had, that the hotter coffee had now been transferred to the room, which is at 70 degrees Fahrenheit. So if you think of your coffee, assuming there is no vaporization or there is no evaporation, if you think of this as your control volume, you had a certain amount of energy in here. So there is no movement of the boundary. So let's just assume that work is 0. You had a certain amount of heat that is stored in the you had a certain amount of internal energy due to the temperature of the hot coffee, and because heat left the system, you are going to have the heat transferred equal to the change in internal energy. And in this case, the heat left the system, so heat would be negative, which means the change in internal energy is also negative, meaning there is a decrease in internal energy. Decrease in internal energy or drop in temperature. This is familiar from everyday life. Something hot cools down eventually over time. But if you think of the opposite situation, you have your coffee at 70 degrees Fahrenheit after a long time. You have your room at also 70 degrees Fahrenheit. We never see or never have seen the cold coffee warming up by itself by absorbing heat from the surrounding, which is either at the same temperature or is even colder. You never see that the hot coffee, the coffee that's at the same temperature as the room, spontaneously picking up heat and becoming hot coffee. You never see that happen. Although there is no restriction on the first law statement that says this cannot happen. There is no reason to think that you could have heat transfer from the surrounding to the system by itself, and that leads to an increase in delta U. If Q were positive, then delta U will increase. That's still possible according to the first law. So a spontaneous heat transfer from the surrounding to a lower temperature to a system that is at a lower temperature a spontaneous heat transfer from the surrounding to a system that is at a lower temperature is not seen in nature, first of all, but is not forbidden by the first law of thermodynamics. A spontaneous heat transfer from the surrounding to a system that is at a lower temperature is not seen in nature, first of all, it doesn't happen, but it is not forbidden by the first law of thermodynamics. So we have a disconnect. First law alone is not enough to completely predict or analyze a thermal system. Why? There is a certain directionality to natural processes. Things always cool down, hot to cold. Things always go from high elevation to lower elevation. Things always roll down a hill. A ball rolls down a hill, but never that a ball that is at the bottom rolls up by itself. That never happens. Hot coffee cools down, but cold coffee never warms up by itself. If you have a let's say a battery and you have a electrical load connected to it, okay, if you supply a current, okay, you can calculate what is the power dissipated by the resistor due to heat. Power dissipated due to resistance, that would be I squared over R. That is, if you put your hand on top of this electrical load, you will feel that much heat being dissipated by the resistor. But you'll never be able to recover this electrical energy even if you supplied the heat that was removed from the resistor. That is, if you ended up heating up the resistor, you cannot produce the electrical energy that was dissipated as heat. So the moral of the story is processes have a direction, and we need a second law of thermodynamics to tell us what the direction is for a given process to take place. So the second law of thermodynamics was stated or devised to explain or to capture what is seen in nature, and there are a couple of ways in which the second law is stated. So I'll just say second law of thermodynamics. We have the Clausius statement, and then we have the Kelvin-Planck statement. Let me first state the Clausius statement, which is, it is impossible to operate in such a way that the sole result would be an energy transfer by heat from a colder to a hotter body. The second law of thermodynamics stated by Clausius is that it is impossible to operate in such a way that the sole result would be an energy transfer by heat from a colder to a hotter body. Now recall your example about the coffee, which is at 70 degrees Celsius, or even you can even imagine a coffee that is at 70 or lower degrees Fahrenheit. Suppose we consider our coffee that is at 70 degrees Fahrenheit and the surrounding is at, let's say, 80 degrees Fahrenheit. I'm sorry. So suppose the coffee is at 70 degrees Fahrenheit and the surrounding is also at 70 degrees Fahrenheit. We wouldn't expect that the surrounding would spontaneously give up heat and make the coffee to 120 degrees Fahrenheit while remaining or cooling down below 70 degrees Fahrenheit. It's not physically possible, and this statement of the second law is simply saying that. It's not proving anything, it's just stating the observations that it is impossible to operate in such a way that the sole result would be an energy transfer by heat from a colder to a hotter body. Now there is another version of the second law of thermodynamics, which is called the Kelvin-Planck statement. It states it is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surroundings while receiving heat transfer from a single thermal reservoir. reservoir. It is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surroundings while receiving heat transfer from a single thermal reservoir. This is a long way of saying it's not possible to convert heat completely to work. That's the short version of the Kelvin Planck statement. Moving on, we spoke about the first law and the second law. The first law, which is an energy balance, and the second law that gives us a direction or natural progression for physical processes. The second law was merely a statement saying some processes or all processes can happen only in a particular way, as in a way to transfer heat from a hotter object to a colder object and not the other way around. It was just a statement stating this is the natural direction and permissible direction for any process. Any process that is in violation of the second law is deemed to be impossible. That is, any process that claims to transfer heat from a colder object to a hotter object is theoretically forbidden by the second law, and so far has not been observed in everyday engineering or physical experiments. Now, we can think of a question that if you take let's say an event like if you have a surface and you drop an egg to the surface, it crashes and breaks. You can watch this movie a million times, you can play this back, but in reality you will never see a broken egg organizing itself and turning into an egg that is unbroken. That is, the reverse will never happen, which brings us to realize that there are processes that are reversible and then there are processes that are irreversible. Reversible processes and irreversible processes. So we need to define what these are. So let's first define a reversible process. A reversible process is defined as a process that can be reversed without leaving any trace on the surroundings. That's the really important point, without leaving any trace on the surroundings. And any process that is not a truly reversible process is an irreversible process. Like, for example, if you have a surface, you have a block, you are sliding the block on the surface. What happens at the interface between the block and this surface here? You have friction. You have friction that basically heats up both the block and the surface. You know this from everyday experience. That is, if you slide the block fast enough, the surface is going to get a little bit hotter. Okay, if you think of your block as your system and the rest of everything is the surrounding, because of your movement of the block along the surface is going to get hotter, or in other words, you have heated up the surrounding. You have made the surrounding a little bit hotter than what it was. Now, if you slide the block back, that is, if you reach this position and then you reverse your motion and slide it back, what will happen? You are not going to get the heat back. That is, you are not going to restore the surrounding to its former state. That is, when you bring back the block here, there is more heat dissipation on the way back as well. That is, friction takes away heat or generates heat in the front stroke as well as the back stroke, and as a result the surrounding gets even hotter. By restoring the block to its original position. That is, even though your system was taken to from state 1 to state 2, from position 1 to position 2, and brought back from position 2 to position 1, you have restored your system to the original state, but you have left the surrounding hotter than it was when you began. So this process is an example of an irreversible process wherein the friction heats up the surrounding and moves it away from its original condition or original state. Now, if you had a block which slides freely on a surface without any friction whatsoever, like we have this magical block and magical surface where there is no friction between them, then in that case you could move the block from state 1 or position 1 to position 2 and you can bring it back. You would have not left any trace on the surroundings because there was no friction whatsoever, and you would have had a truly reversible process. So let me write a statement. So the possibility of a process being reversible simply rests on being every step of the process being reversible and without any irreversibilities. Essentially, this statement means all real processes are irreversible to varying degrees. That's the only difference. They are all irreversible. They may be more irreversible or less irreversible, but they are irreversible. All real processes are irreversible to varying degrees, and that what we call as a reversible process is an idealization that is used as a reference in analysis. It's not something that's found in nature. It's usually a reference in analysis as the ideal case, that no real system can attain it, but we wish to attain it. So that also tells us there are irreversibilities in real world processes. The main irreversibility that we encounter often is friction friction could be between solid and solid, like the example we saw. It could be between solid and fluid, like flow past a surface, or it could be between within the fluid due to viscous effects or velocity gradients. It's very common for us to think of friction. If you have a piston and a cylinder, okay, you have a gas here. If you think of your control volume to be the volume within the piston, you have friction everywhere. You have friction when the piston slides against the walls of the cylinder. You have piston, or you have friction or viscous effects within the gas, and you have viscous effects between the gas and the wall of the cylinder. So you have gas wall, you have gas or viscosity, and you have cylinder and piston surfaces. So you have all types of friction. That's why if you do a certain amount of work, let's say you do a certain amount of boundary work by compressing the cylinder, there is some heat generation at the boundary. So I'll write this in a separate page. So if I have a piston and I compress it from say V1 to V2 P dV, that's the work I do. There is heat generation at the surfaces. Wherever friction acts, friction generates heat. So that is heat that leaves the system. If you have very poor insulation or no insulation, that is heat leaving the system. So you have Q minus W equals delta U. That is, if you had no heat transfer, if you didn't generate any heat, if Q equals 0, the delta U goes into is the delta U, or the increase in internal energy of the gas is due to the work done, or all the work done goes into heating up the gas. All the work done heats up, or not, I shouldn't say heats up, all the work raises the internal energy of the gas. But if Q is not 0, then you have lesser amount of energy available to raise the internal energy of the gas, or in other words, some of your work input that you put in has been wasted because of friction. So irreversibilities always cause undesirable effects that we wish to mitigate, and we'll see more about this in examples. Another type of irreversibility is the unrestrained expansion of a gas. Now, why is this an irreversibility? If you have a gas that's highly compressed, like for example this could be CO2 that's highly compressed, and you are locking this down by applying forces, if all of a sudden you remove these forces, so if you have restraining forces, if all of a sudden, if we remove the forces, you are going to have the gas push back against the piston and let it freely expand. So you have the gas pushing back and you have unrestrained expansion. If you expand too fast, what happens? If you expand too fast, the pressure drops quickly, which can cause the system to cool down. So the expansion will cause the pressure to drop. First of all, a drop in pressure is accompanied by a cooling or condensation, which causes cooling and causes heat to leave the system. Heat to leave the system. Heat loss. Okay. Now what that means is you have a certain amount of gas with a certain energy content delta U, and because of the heat loss, the energy content of the gas is irreversibly lost. That this heat loss is irreversible. It's not coming back when the system comes to a stop, or when the gas stops expanding. So this irreversible heat loss is a consequence of unrestrained expansion. The third form of irreversibility is heat transfer, which is, again, like I said, because it's a direct consequence of the second law. If you have hot object, it cools down, but whenever you have an object that's not hotter than the surrounding, it never spontaneously warms up. So it always flows one directionally. Another type of irreversibility that is encountered is chemical reactions. Although in this course we don't see much of that. Like for example, if you had a fuel, carbon, and you combusted that, you get CO2 plus heat. Now if you take CO2 and you just apply the same amount of heat, you're not going to get the carbon and oxygen back. This doesn't happen. Usually chemical reactions are irreversible, although we won't deal with much of that in this class. Now within reversible processes, we want to distinguish between what is called as internally reversible and externally reversible processes. Now what is internally reversible? If a process is called internally reversible, if no irreversibilities exist within the boundaries of the system, within the boundaries of the system during the process. And an externally reversible process is one in which if no irreversibilities occur outside the system boundaries during the process. If no irreversibilities occur outside the system boundaries during the process. Now let's bring that example back. You have your block, it is at position 1, you take it to position 2, and then you bring it back to position 1. Okay, 1 to 2 and back. Okay, now during this trip within the block, if you consider the block to be your system, we are just moving it from 1 to 2 and bringing it back. Within the block, which is basically a solid, there is no friction or any other irreversibilities in this case. There are no other irreversibilities. Okay, so this would be an example where this is internally reversible. But if you think of the surrounding, that is the surface got hotter due to friction and heat transfer. So the surface, as far as the surrounding is considered, this process is not externally reversible. If you don't look at the surrounding, this process is internally reversible. If you look at the surrounding, this process is not externally reversible. A process is reversible if it's both internally and externally reversible. Most processes that we can think of are irreversible, but many of them are at least internally reversible. So most are irreversible, period. Okay. Many are internally reversible. Many are internally reversible, but they change their surrounding irreversibly. And then all processes in nature are irreversible because because no processes are externally reversible as well. That would be an exception that's not been found so far. So moving forward, what have we seen so far? We have seen that the second law talks about a natural direction for processes. In that based on that, there are reversible and irreversible processes. That is, what we can understand from that is any like if you take a particular state 1 to 2, okay, could be on, let's say, PV coordinates. There is a path from 1 to 2. There are an infinite number of paths from 1 to 2. You could take any path to go from 1 to 2, and then there is one path which is reversible, and then there are many others. There is a reversible path, and then there are many others that are irreversible. Now all these irreversible paths, they differ in each other in the degree of irreversibilities. These differ in the degree of irreversibility. They differ in the degree of irreversibility. Now, if you have a need to go from state 1 to state 2, you want to choose the path that is the most closest to being a reversible path. Okay, just keep that in mind. Any good engineer would design the path 1 to 2 as close as possible to being reversible to minimize energy losses. Now, what do I mean by that? Suppose you have Q minus W equals delta U. You want to make, if you are transferring a certain amount of heat, let's say you are transferring a certain amount of heat, the heat that leaves the system is usually due to the friction or the irreversibilities. due to the friction or the irreversibilities. Now, if you want to convert this heat into either work or internal energy or both, you want to make sure that the heat loss is minimum. You want to make sure that this Q out term is as small as possible. This is if you want to design a process, you want to restrict or reduce the amount of irreversibilities such that all the heat that you provided goes into doing something useful like work or raising the internal energy of the system. Okay, and why do you want to do this? Because Q in is the heat that is input, okay, and that's directly related to the energy bills. The heat input is directly due to the amount of fuel that you combust to create that heat. So you don't want your energy to be wasted, because that will incur more cost, and that's, as engineers, that's what we look out for. The other situation is if you have a piston, like for example, if you try to do work on the gas and this is your system, again the heat that leaves the system is due to the friction or the irreversibilities. And if you think of Q minus W equals delta U, if you do work, if you want to raise the internal energy of the gas, you want this to be as small as possible so that all the work that you do is converted into internal energy. And this work is, let's say, done by connecting to a horse and wheel, or it's connected to a cycle like a bicycle, or it's connected to a motor. Whatever it is work that you do mechanically, and you have to expend energy for that, which comes with the cost. So this is directly related to the energy or the money that you spend, and to get useful outcomes out of it, you need to minimize the irreversibilities in this system. Moving on, in the spirit of processes, we want to look at what is called as a cycle. Okay, we saw that a process is one that takes you from a thermodynamic state to another. So if you have P, you have state 1 and you have state 2. Okay, that is a process. Now a cycle is one in which you could have multiple states that you visit, 3 and then 1. So if you go from 1 to 2 to 3 and back to 1, that is at the end of a cycle. At the end of a cycle, the system is restored to its initial state. That would be a cycle. And to go from one state to another, we have different processes. These processes could be reversible, they could be irreversible, but at the end of the cycle, the system comes back to its initial state. It may be having a lot of intermediate states. Okay. Now, one reason why we define cycles is that we like to have devices like, for example, heat engines that operate in a cycle, to produce mechanical work that produce mechanical work from the heat energy of a working fluid. Okay. Now, what is this heat engine? Obviously this heat engine operates in a cycle. You do know that because your IC engine that runs your car basically has this 4 strokes, where energy of the fuel, energy or chemical energy of the fuel, to be very specific, chemical energy of the fuel of the gasoline is converted to mechanical energy that drives the wheels, that makes the wheels spin. There is a lot of energy conversion steps from the chemical energy of the fuel to the mechanical energy that drives your car. And you can think of, if there are multiple processes between these two end states, they can be reversible, they can be irreversible. Within irreversible, they can be slightly irreversible, they can be moderately or extremely irreversible, making the process cost effective or not cost effective. So we need to understand what is the ideal way to, or what is the way to operate a heat engine, and then the ideal way to operate a heat engine, so that we can understand how far are we when we design real processes. Okay, so first of all, what is a heat engine? A simplest heat engine that you can imagine is also depicted in figure 610. Okay, it consists of 4 components. The simplest heat engine can be constructed with 4 thermal devices, one being a boiler. Let's say we start with a boiler where you produce hot steam. So from the boiler you have hot steam, you input energy as heat, you vaporize the water, turn it into saturated vapor or even superheated vapor, and then you flow the steam onto a turbine. A turbine expands the hot steam at high pressure. It converts the internal energy and kinetic energy of the fluid to mechanical energy, which is shaft work. So you input heat here, you extract work here. Okay, so from the turbine you have, going into the turbine you have high temperature, high pressure steam, and coming out of the turbine you have spent steam, which is usually high temperature and low pressure. Okay, have spent steam that's coming out, and then you have what is called as a condenser. Okay, in the condenser you have this is usually a heat exchanger with a lot of winding tubes, wherein the surface area is increased so that the low pressure steam can give up heat and start condensing. So it's a place to reject heat. Okay, usually it's exhausted to the atmosphere, and then coming out of the condenser is low pressure, low temperature, water, and they come back here. They go through a compressor, where the low temperature, low pressure water is compressed, wherein you get high pressure, low temperature water, and that goes into the boiler and the cycle continues. Okay, so this is a place where you provide work. You provide shaft work, so you input work. So you do work at the compressor, you provide heat at the boiler, you produce high temperature, high pressure steam that is then converted into turbine, which is converted into mechanical work at the turbine, except that this turbine work output is much bigger than the shaft work input, leading to a net work output out of this cycle. So in this cycle, the net work output is the out plus in. This is usually a negative number, this is a positive number, and the heat net or the net heat transfer is Q in plus Q out. This is Q in is the one you add at the boiler, it's usually positive. Q out is the heat that is rejected at the condenser, which is usually negative. So a heat engine is really a system that converts the thermal energy into mechanical energy, and it requires at least 4 components identified here to carry out this process. So what would be the efficiency of such a system? So if I write work net is work out minus work in, and Q net equals Q in, I'll write plus Q out. Okay. Now if you think of the boiler, you provide the heat there. If you think of the condenser, the heat is rejected by the fluid to the surrounding, and usually this is irrecoverable. That is, you just eject the heat. If you have your car radiator, the fluid, the hot water dumps the heat through the car radiator into the atmosphere, and you don't get it back. It's done, it's gone. So it's not something you can reuse. So whatever heat you provide at the boiler is really not connected to the heat that is dumped at the condenser. So we can say that this is the dollar that you spend. Okay, this is the dollar that you spend. This is related to the energy bill that you would get by providing heat. At the turbine, you extract certain amount of work as shaft work. You have a rotating shaft that's at a certain RPM. You can use it to drive some other machines like a camshaft or an electrical generator or so on. At the compressor, you input work. You have to drive the compressor by applying electrical power or some other mechanical power, and this is again related to the dollar that you spend. Okay. Now the net work output that you get, if you are trying to use this heat engine to produce mechanical work, that will be, let's say, like a generator that will run a portable home generator, or that will run an IC engine. The net work output is what is important, because this is your dollar that will get in value. This is the value that you will get for your energy bill. So if we think of the work net output divided by the heat input, this would be the efficiency of conversion from heat to work. Okay, and this is formally called the thermal efficiency, which is the net work output divided by the net heat input, the net work output being the the work output plus the work input divided by Q in. Just remember the sign convention for work. Work is positive if it is done by the system, and heat is positive if it is transferred to the system. Okay, so this is the thermal efficiency of a heat engine. Okay, and let me rewrite that here. This is work output plus work input divided by heat input. Okay, so for the whole cycle, what do we have? Whatever your intermediate steps are, you can write Q net minus W net should be equal to delta U for the cycle. Now delta U for the cycle is 0 because initial state is same as the final state. This is simply U1 minus U1, making it 0. So you have Q net equals W net. Okay, that is Q in plus Q out equals W out plus W in. So if I substitute in thermal efficiency, this is Q net divided by Q in, which is Q in plus Q out divided by Q in. This is 1 plus Q out divided by Q in, the thermal efficiency. Remember that Q out is a quantity that's negative by our sign convention, so the plus sign is really like writing 1 minus the magnitude of Q out without the sign divided by Q in. Okay, so I'll write it again neatly. Thermal efficiency is 1 minus magnitude of Q out divided by Q in. So if you input certain joules of energy and the heat extracted from the condenser is certain joules, you can simply calculate the thermal efficiency using the formula here. Okay. Now I've told you that the heat engine consists of 4 steps, one being a heat addition step at the boiler, and the other is being an expansion step or work extraction at the turbine, and the third being a heat rejection or heat removal at the condenser, and the fourth being a compression or work input step at the compressor. Heat engine consists of 4 processes that together make a cycle. Okay. Make a cycle. Now, you have 4 processes. The next question is, can we make these processes, either they are, well, ideally reversible. If you make them reversible, that would be the best world, and or at least as less irreversible as we can. We don't know how to do the latter. We don't really know what is the best way you could do this, but at least we can do an analysis that gives us the thermal efficiency, which is, you remember, 1 minus Q out divided by Q in, which is the maximum possible efficiency that you can attain. You can at least calculate what is the efficiency of this cycle when you have a reversible process. You can at least calculate this. Okay, that's what we are going to do next. We are going to calculate the efficiency of a reversible efficiency of having reversible steps in a heat engine cycle. Take for example step 1, which is heat addition. What's the best way to add heat, or what's the most irreversible way to add heat? That's the question. What's the best way to add heat? That if you ask that question, so to recognize or to identify the ideal ways or reversible ways to carry out the different steps in this heat engine cycle, the French physicist Sadi Carnot, he came up with these steps. So for heat addition, a reversible isothermal heat addition, isothermal, wherein the temperature is constant, it is equal to the temperature of the hot reservoir. That is, like, for example, if you have your boiler, let's say you are transferring heat. If you have a temperature of the reservoir at TH, you want to make sure that the temperature inside your system is also TH, so that the heat transfer takes place at the maximum efficiency. So reversible isothermal heat addition, okay, and then the second step being the expansion. Actually, let me back up a little. So if you are thinking of heat addition, you have Q minus W equals delta U. If you have isothermal heat addition, this term is 0, so that all the heat you added turns into potential of the gas to do work. So Q equals W. The second step being the expansion, we want to do that as adiabatic expansion. What is adiabatic? Recall, the heat transfer or heat losses is 0 due to proper insulation. So you have Q minus W equals delta U, or in other words, all the internal energy of the gas goes into being converted into mechanical work. That is maximum conversion to work. So for the second step, we want to do an adiabatic expansion, and for the third step, we have isothermal heat rejection for the same reason that I mentioned before, and the fourth step being adiabatic compression, so that all the work input that you put goes into increasing the internal energy and is not lost at heat. So if I depict this in a PV diagram, pressure, specific volume, I have process 1 proceeding at constant temperature to state 2, okay, and from state 2 I have an adiabatic process in which heat loss is 0 to go to state 3, and then from state 3 I have an isothermal process which is a heat rejection to state 4. This is again TL equals constant, and then from 4 to 1 I have another adiabatic process in which heat loss is 0, that is adiabatic compression. So these four isothermal heat addition and rejection and adiabatic expansion or compression, this represents the most ideal way or reversible way you could do this heat engine cycle, and this cycle is called the Carnot cycle. The figure that I drew in the last page, which is also in figure 6-37, is called the Carnot cycle, okay, and you can derive an efficiency for the Carnot cycle as 1 minus, we do know that this is equal to Q out divided by Q in. This is equal to 1 minus the temperature of the temperature at which heat rejection takes place divided by the temperature at which the heat addition takes place. So this is the heat rejection temperature, and this is the heat addition temperature. So this is something you should remember, because we will always use the Carnot efficiency. Carnot efficiency is the maximum possible theoretical efficiency. Now, so far we have looked at a heat engine. A heat engine is a device that converts heat into mechanical work. Now we want to think about the other type of device that is very common in thermal engineering, which is a refrigerator or a heat pump. These are devices that remove heat from a system or a volume when mechanical work is provided externally. These are essentially the opposite of heat engines. A refrigerator takes heat from a environment and dumps it in a surrounding that is at a higher temperature. That is, this you could think is in direct violation of the second law, which is if you have a volume or a system that is at a lower temperature and a surrounding that is at a higher temperature, second law states that you cannot have energy transfer between the low temperature system to the high temperature surrounding without external work. Without external work, it's not possible. Heat would flow only from the higher temperature to the lower temperature. But with external flow, it is possible to transfer or shovel heat from a lower temperature system and dump it into a higher temperature system. This is like, metaphorically speaking, you have a ditch, you have a crane that puts its jaw inside, excavates the mud and removes the mud and piles it up on top of a heap to remove more and more earth and move it onto a heap. This is the thermal version of that, where you excavate heat from a low temperature system and dump it into a higher temperature surrounding with the help of external work. In the case of the earth moving, it's the crane. In the case of the thermal system, it's the refrigerator. You could draw a schematic of the refrigerator by almost literally reversing the schematic of a heat engine. Like, for example, we start the refrigeration cycle. So I'll just write refrigeration cycle, where we have a compressor wherein we input work, we produce refrigerant, we take the working fluid and turn it into high pressure, high temperature working fluid. It is then transported on to a condenser, where the high temperature is dumped where the high temperature is dumped. So heat leaves the system here, It's usually dumped to the surrounding air or the outside of a building, and you get high pressure, low temperature, or high pressure, low temperature working fluid, and that then passes on to an expansion valve wherein the working fluid undergoes expansion, and that expansion produces cooling, and then you get low pressure, low temperature working fluid, and this goes into what is called as an evaporator. So remember, this is low temperature, the heat from the system that you want to cool down. So suppose this is the heat, this is your car or your living room. So you want to let the heat flow from the hotter car or the hotter living room into the evaporator, where this low temperature, low pressure refrigerant is warmed up, and it becomes low pressure, warmed up, and typically this undergoes a phase change here. The word evaporator is used to denote that the heat transfer takes place by phase change. Usually this is like a liquid, and if you heat up a liquid at the same temperature, you get saturated vapor, okay, and the cycle goes on. So this is the space that you want to cool down, this one. You extract heat from it through the evaporator. You send the refrigerant as a vapor into the compressor where it's pressurized, and the pressurized working fluid is sent to the condenser where it dumps its heat, reduces in temperature, and then the low temperature, high pressure working fluid or refrigerant is sent to an expansion valve where it is brought down to low pressure and low temperature by sudden expansion. It is usually modeled as adiabatic, and the cycle goes on, producing the desired refrigeration effect. Just like we defined a thermal efficiency for the heat engine cycle, we are going to define a coefficient of performance we'll call it COP for a refrigeration cycle, and this COP is defined as the desired output divided by the required input. Now what is this desired output? It is the heat that you can extract from the system divided by the required input, which is the work net. It is the difference between the compressor work that you need to do and the expansion valve. The expansion valve usually is designed without moving parts, so it's usually the compressor work that you need to input. Okay. Now this is also a cycle, so you can write that the work net, the Q net minus the work net equals delta U, which is 0, and the Q net is the heat in plus the heat out with the sign convention. Okay. Remember, this is where this is your evaporator, and this is your condenser. Okay. So I have the coefficient of performance for a refrigeration cycle to be QL divided by QH minus QL equals 1 over QH over QL minus 1, where QH is your heat input is your heat input, that is the heat that is removed the heat that is removed from the room. I think I'm going to pause. So I'm sorry about the last few seconds. Let me try again. QL is the heat that is rejected at the condenser, and QL is the heat that is added to the working fluid at the evaporator. Okay, at the evaporator. So the formula COP equals QL divided by QH minus QL is something you could use for solving problems, and we will use it in due course. To wrap up this unit, or at least this chapter of the module, we saw what is the second law. We saw what are reversible and irreversible processes. We saw what is a heat engine, what is the ideal heat engine or the Carnot cycle. We also saw what is the efficiency of a heat engine. And then we also saw what is a refrigeration cycle. And then we saw what is the coefficient of performance for a refrigeration cycle. This is what we are going to be considering for this course. There are more topics that I have not covered, but this is what is fair game for our exam. Lastly, I want to list all the section numbers that you should look at. 6-1, 6-3, 6-4, the Kelvin Planck, and Clausius statements. Okay, and you also want to look at section 6-6 and the Carnot cycle, which is section 6-7. So these are the sections that you must be reading. There are certain special figures that that I would like you not to miss. Figure 6-10, figure 6-19, figure 6-36 and 37. You should also go through the chapter summary that is listed in page 311 of chapter 6 of the textbook, 8th edition, Sengel and Bowles. So this will allow you to understand the concepts. Please watch my video. Please go through the textbook. If something is not clear, please raise that during class, and also you can set up meetings with me to talk about things. We will do example problems related to this unit during lecture time. Thank you.